Welcome to the Ezra seminar this week. So we are delighted to have Professor Nils Napp join us. He started his career at UW doing self-assembly with robotics. And then he moved on to Harvard and really sort of branched into construction with amorphous materials and continued that work as an assistant professor at University of Buffalo, for which he received numerous Best Paper Awards, one at DARS, and nomination at the Robotic Science and Systems Conference, which is very prestigious. He also, for that work, received the prestigious NSF CAREER Award. And that sort of funded ongoing work. And as soon as he got that CAREER Award, we cleverly poached him into ECE. So he's one of our first, our most junior robotics faculty in ECE. Since getting to Cornell, he sort of followed the traditional trend of robotics professors here, which is he's branched into robot design synthesis, LAM, working with bioreactors, working on pollinator monitoring. His most recent work was featured in PNAS on honeycomb construction and constrained geometries. I think we're going to hear mostly about construction today, but it should be a great talk. So please help me welcoming Nils.
Peterson is also a co-author on the PNAS papers. Good advertising. Thank you for the introduction. So the title of the talk is, first of all, if you're online, I think Kirsten will monitor the chat, and feel free to interrupt and ask questions. I think if we get bogged down with time, we can always skip some of the later stuff. So we can make this more interactive. I think that is more fun. So I'm just about the title. I want to explain where that's come from. So this is one of the sort of go-to textbooks by two eminent Cornell professors on algorithm design, both in the computer science department. And in algorithm design, you have all these great abstractions, right? You have abstractions for computation, where you start with like digital logic that behaves in really predictable ways. You can kind of turn digital logic, you make logic blocks, you can turn that into processors, and then you can get these sort of higher and higher level programming languages in which you can get sort of this like really predictable behavior to do really complex stuff, right? In algorithm design, you look at like time complexity, runtime, space complexity, and all those kinds of things. And it would be great if we can have like that same power of abstraction with robotics. And to me, like the picture is on this textbook is beautiful and also a little bit incongruent, because I, as a roboticist, also I collaborate with biologists, look at this, and it's not really clear to me what the birds are doing. Like they're trying to build a nest, and presumably they have some sort of rule set for doing that, right? It probably involves some kind of weaving, going over, going under behavior. But it's really difficult. I think it'd be really difficult to model that accurately, right? And if we wanted to design like a bird weaving algorithm, it's not really clear sort of at what level we need to model this, right? So if you look at blades of grass, right, they often have little hairs on them, so they have this really complicated friction behavior where there's more friction in one direction than the other. Friction obviously plays a part in holding this thing together, right? And it's not really clear like how accurately you would need to model the friction behavior of each blade of grass. The glass, like, if you played with sticks and little leaves of grass, right, they have sort of this flexible regime, but then if you pinch it too much, right, like all the cells break and you get this little hinge. And all of those could potentially play a role. So if I wanted to make like a weaving algorithm, a robot that follows a weaving algorithm to build these types of structures, right, it's really hard to figure out like where, sort of at what level of detail you need to capture this behavior. Probably it's not the right approach to try to fully model like all the friction and all the formation in each blade of grass, but we want sort of some model of the environment that captures some of these essential behaviors. So I want to motivate this talk, try to figure out how we can think of robots as embodied algorithms. So if I design a computer algorithm or program, right, all the memory in the computer has a state before the program runs. And then I do algorithm analysis to try to figure out what the state of the program of the memory is afterwards. And I press run, and then I expect sort of really predictable outcomes. And we can almost think of robots as the same way as acting on physical space. So most robots do like physical work on the environment. We program them, to like do specific things. And ideally, right, the world will be in a particular state before. Then we want something to happen, so we program this robot to accomplish those goals. Then we press play. And then after the robot is done, right, the world is in a different state. So I'm thinking of robots. I want to be able to like think of robots as these embodied algorithms where we get really predictable behavior. And to do that, we need sort of the right abstraction barriers. So we can reason about like what the actual outcome of robots behave, like sort of robots manipulating their environment is, and get sort of predictable long-term behavior. Focusing on environmental modification, I think is both interesting because it kind of makes robots different from just programming, because there's something happening in physical space. And there are sort of immediate practical applications for robots manipulating their environment. Sort of one like really obvious application is construction. I'm going to talk a little bit about like robotic construction platforms, where there is an immense need for better construction techniques. So these numbers are not like the latest numbers, but from a few years ago. So they probably have changed, but they probably haven't gotten better. Right. So in the near term, like 12%. So a large fraction of the human population is expected to move into cities. A lot of the population growth we expect to be in developing countries that already have severe housing shortages. There are a lot of displaced people, where the populations move changes. And in addition to building housing, right, like there are really alarming things going on in climate change, so that the infrastructure we need in the foreseeable future, like, probably looks really different. It would be great if we can make like just construction sort of faster and more safe and more flexible. It's not on here, but the construction industry is also super dangerous, so it's actually a space where several companies are trying to use robotics, because that's the sort of traditional place where we would want to use robotics, sort of dirty, dull, dangerous, and construction hits all of those. Is there a chat question? Or?
No, that was me posting.
Perfect. Okay. So I'm going to talk about 3 different types of abstraction barriers that we've worked with in our lab, and then robotic systems we built around each one of these abstraction barriers.
So if you want to click on your slides, that bar will go away.
I'm not sure.
If you pull up the chat and close it again, the bar will go away.
Huh?
If you pull up the chat and close it again, the bar will go away. Sorry about that. There we go.
Cool. So the first one, I want to look at sort of discrete rigid assembly. And that is a pretty common model for construction systems. So here's some pictures of sort of research-grade construction systems where individual robots manipulate sort of rigid prefabricated building materials. Normally, like when we think of these systems, it looks like these things are built sort of like a house, like brick by brick. So robots add individual components one at a time, as opposed to self-assembly, where it gets sort of large subcomponents that assemble. Agents, sort of on the research side, a lot of the work is on figuring out how to make this a distributed operation. So often we assume that the construction agents don't have access to the most current sort of up-to-date state of the world. Instead, they need to make decisions based on sort of local sensing ability to build these large structures. But one thing that inevitably happens in these situations is that there are sort of really strict assembly order constraints, because the things are rigid. And to fit things together reliably, you often need a sort of alignment features. And it's these alignment features that mean like I can't sort of slide something into a constrained place. On the sort of commercial side, also on the rigid prefabricated building materials, this is a picture of the semi-automatic mason SAM This is made by a company called Construction Robotics that's in Victor, New York, a few hours north of here. And they have a similar problem, right? Sort of from an assembly planning perspective. There is a picture that an architect or designer came up with that's on the top left. And then the sort of system needs to figure out some specific order to put these together. If we look at this, the sort of one of the research construction systems that Professor Peterson worked on and that we collaborated on afterwards is the Termi's distributed construction system, where I have sort of individual robots crawling around on a partially completed structure. And the problem there is the robots don't have access to the current construction state. They do know the target structure, and they do know sort of the X, Y, Z location of where they're currently at. And the sort of problem here is that we need to break down sort of this global goal into a whole bunch of locally checkable assembly rules that follow precedence constraints. And the thing that's really easy to do is it's really easy to actually sort of follow, create partial assemblies that will necessarily create deadlock, where I sort of start something in two different locations, and if I do that, then I like have a situation where like the physical order, assembly order constraints don't allow the system to make progress. So we need to be really careful on how we break this down into locally checkable rules. And sort of in this work, what we're doing is we're breaking this down into pairwise precedence constraints between locations, and these then form this directed acyclic graph that we can also describe as a partial order. I'm going to talk more about that in a couple slides. And we can generate these rules relatively efficiently in such a way that they also maximize the parallelism. So by that I mean that there's sort of as many ways as possible to go through the system so that as many robots as possible can make progress on this, building this shared structure. This, now if I look at sort of the original problem that like an industrial assembly robot has, like SAM, these kind of look similar, right? I have now sort of this discrete space I can work with, and each discrete building element, I know where it should be in the end, so I can just like represent it as being there or not being there. And when I think about coming up with an assembly order, all I really do is give an order on these states, right? So on the left, you can see the assembly order that Sam would, like a robot like the bricklaying robot would normally follow, where I pre-compute a specific order, right? So there's sort of one dependency chain that goes back and forth and assembles all these blocks. On the right is sort of the same discrete space with the same physical precedence constraints, and we applied sort of this Termi's partial order precedence constraint compiler to it. And there are sort of some practical benefits for why it would actually make more sense to use a plan like the one on the right on a system like SAM. So, for example, assume you laid like the first course of bricks, so the first layer, so 1, 2, 3, 4. And then one thing that happens in construction sites fairly frequently is that you get sort of like these events that like exclude people, right? So for safety reasons. So for example, if I have a crane that's moving a really heavy load, then people are not supposed to be on where the crane is going. So they're like, you know, whoever the safety manager is will like put up some cones or some tape. That means that like if this location becomes temporarily inaccessible, if I have a single plan, right, suddenly all of these states become something that I cannot reach. And really quickly, the robot just needs to sit there and wait. Although, you know, in theory, it could make progress. And if I try to come up with this partial order and have the same thing blocked starting from the same state, I suddenly have a much larger area in which the system can still make progress, right? So even if I have a single robot kind of executing this parallel assembly plan, there is a benefit to trying to break down this problem into something where I can make progress many different ways. Now, thinking of the sort of assembly rule set as a partial order also gives us some nice tools, just because partial orders are a really well-studied mathematical object that come with a bunch of tools. So just as a quick reminder, a partially ordered set, or pose set, is a binary relation that's reflexive, anti-symmetric, and transitive. So it really behaves like the less or equal operator, like you'd want it to behave. The big difference to a total order that you'd be familiar with, like on the real line, is that in a partial order, not all sets are relatable, right? So if you give you two real numbers, I can always relate them as less or equal to. But in a partial order, there are some elements that that relation just doesn't make sense. So a really common one is the subset relation, right? Where some sets are subsets of others. But if they have like a non-empty intersection, or if they're not strictly subsets of each other, right, like you can't really compare them with this relation. Here, the assembly sites have the same property, right, where if you look at this, I don't know if you can see that from the back, but there's a 1, then location 2 and 9 can happen after 1 happens, and 8 can happen only after 2 and 9 happen. But 9 and 2 are not directly related, which means that I can kind of independently choose to make progress because they're not really dependent on each other at all. But then other things can sort of depend on those elements. So this is why this is a partial order. So if we look at sort of the properties of partial orders, we can maybe illustrate this on a really simple sort of toy system to see what we can do if we start thinking about these assembly rules as partial orders. So let's say I want to assemble a square. These are the XY locations of this larger square. It's 3 by 3. And I have this physical sort of assembly rule that is a sort of restriction on the assembly that I can't move a block into an area that's constrained from 2 sides. And that's a really common thing for a whole bunch of discrete assembly type systems. So in a system that's small enough, I can now go through and say, with this physical restriction, I can actually enumerate all the possible partial assemblies I could have, following the specific sort of physical thing that I'm not allowed to do. This gives me another partial order again. So you can think partial order is like there's a one-to-one mapping between a directed acyclic graph and a partial order. So this is the Hass diagram. These are called Hass diagrams then. This is like the graph you would get for just applying this rule that I'm not allowed to put 2 things between a location, one thing between to a location where the 2 sides are already assembled. If that's the only thing that goes on, then these are all the partial states I can reach. So for example, this particular state, the x's correspond to assembled locations. The grayed out areas are not assembled. So this is x is down here, and then 000 up there. So this is the diagram that I get if I with the only restriction is this physical non-insertion restriction. And I can compare that to sort of all the states that I'm able to reach if I follow this distributed assembly program. Right? So the distributed assembly program also has the same physical restrictions, right? But there are other restrictions that are only there because of the way that I program these robots. So in particular, I'm using this example, then I'm passing it through this like assembly order, partial order compiler. Then this is the sort of assembly order, partial order that I get out of this. So I first need to start with 0, 0, then I can either do 1, 0, or 0, 1, but I need to do 1, 0 before I can do 1, 1, right? So when I sort of fan out, it's pretty easy because everything only has like sort of one thing that it depends on, but then I get these joins up here where things come back together, right? And here, even if I got to this location and this one was assembled, I have to wait, right? And these are the kind of things that like make this distributed assembly potentially not like super efficient, and the kind of things that we optimize for. Now, from this partial order, I can compute what is called the order ideal, which is the set of all down sets, which just means that like this is another set, and every element of that set is a set, and the set contains all the things. If it contains this one, it must contain all the ones that come before it in the partial order. And right? So and that like kind of directly corresponds to the set of partial assemblies that I can get, because it means that if an element is in that set, right, then all the things that came before it that must have been assembled before are also in that set. Now, here I can enumerate this, right? And you can see that this is a subset of that. But the order ideal has like this really nice recursive formula where I can compute the size of the order ideal without actually having to enumerate all the elements. Because enumerating all the elements, this becomes exponentially hard. I can only do that for really small examples. But now this gives us like a really nice way of analyzing the whole construction mechanism, right? Where there are 3 lines or 4 lines here, right? This is sort of the number of states that I could potentially reach, right? It's 1 if I only have a single plan. This is a single plan, right? Like it's not 1, it's the number of, it's like n, whatever the number of parts is. The dotted line up here is if there are no assembly order constraints at all, right? If I can have floating bricks, I can put them in any order, then it's just 2 to the n are the number of possible states I can reach. And here in the middle is the number of possible states if I only take into account the sort of physical assembly constraints. And right under it is the number of states that I can reach with this action partial order, which correspond to the number of states I can reach following this distributed construction algorithm. So by thinking of this as partial orders, we can also like sort of directly compute like how well is this like discrete material matched to the actual program, right? Like, because I can also program the robots so that there's only a single plan, but then I'm kind of like really constraining the system in a way that's totally artificial and only because I program my robots in a proper way. So these are kinds of nice things that we can do if we think of this, if we think of things as partial orders in sort of this discrete rigid assembly state. So. Right, so we developed this general purpose compiler. We also used like the sort of the same idea for other distributed construction algorithms with different groups, and then we're able to try to like figure out sort of in these distributed construction setting like how to maximize parallelism and how like figuring out like how like analyzing this behavior like the runtime behavior of the system in a little bit more formal way. Okay. I'm going to move construction material representation. So if there are any questions about the discrete stuff, just interrupt me. Yeah?
Yeah, I'm trying to figure out if there's another constraint associated with the physical embodiment with the parallelism, is that there actually has to be, I mean, imagine there's multiple robots that are going in, and they have to sort of be in the place where they can then execute the next.
There are. I mean, absolutely.
Right, so there are other constraints that are not part of what you were describing there.
Yes, absolutely. So it doesn't really take, right, like it only counts the number of states, but it doesn't really deal with like, it could just be one robot going through by itself.
Right.
So, and that sort of actual parallel construction has more stuff going on, right? Like there's normally a single entry point, which is like one of the things that we're trying to figure out if you can deal with that. So like the amount of parallelism you can get is even limited by that. Yeah, that's a great question. It's also nice to see you in person.
Nice to, yeah, see you in person, by the way, right?
Cool. So the next one. So we get a lot of cool math tools for this, right? But the types of things we can build is also a little bit limited. So next I'm going to look at construction materials that are like kind of hard to model and deformable in order to deal with more unstructured terrain. So a dirty, dull, dangerous, so that's where you want to use robots. So ideally we want to put robots into these types of situations. So this is like a earthquake disaster site. Super dangerous for people to be there. Because these things like the buildings are damaged, they could collapse, so you don't want people next to them. You still want to explore the space, you want to potentially repair some things, you want to make stuff navigable for rescue crews. So it's exactly where we want to use robot. It's just really hard to use robots in this type of environment. If we look at nature, so the abstraction barriers I'm going to talk about now are trying to enable systems to work in this type of environment. So if you look at sort of biological construction systems, they're actually really good at dealing with like totally unstructured, terrible environments. They work in huge groups spanning many orders of magnitude and also sort of build structures relative to their own body size over many orders of magnitudes. So we're trying to find out sort of like what makes this work so well and design robotic systems that mimic some of these properties. So one of the things that all of these animals seem to do is they have this sort of like immediate feedback on function, right? Where it's not like they have an open loop blueprint and then they just like build it over many, many steps. Instead, they constantly sort of sense their environment, see if it looks right, like, you know, modify it, add more things if it doesn't quite work. And if something breaks, like they kind of fix it the same way that they build it. So it's this like sort of constant feedback with the environment on what presumably is the sort of functional, the function of the final structure. In a lot of these systems, like there's not even consensus on what exactly these structures are for, like sort of how they evolve. So it's often really hard to actually map this directly to a function. There are some examples, for example, in beaver construction where we know, like, we kind of know what the function of the dam is, and we kind of know what the cues are, and those are kind of tied together in this really nice way, right? So rushing water will make beavers build. If you put like a tape recorder of rushing water next to a beaver dam, it will just like cover it up overnight. Similar, if there are sort of notches in the horizon, they will fill those up, right? So, and if you got rid of all the sound of rushing water and of all the horizon notches, you would have a dam. So to make this a little bit more concrete for something that we could sort of actually work on, we kind of boil this down to a very specific problem, which we call the adaptive ramp building problem. And the problem is we want to send like you know, one or more robots out that have local, mostly local sensing information, and that's indicated by these dotted red lines. This is the range at which the robots will closely monitor their environment and use that to make their decisions. And we want the robots to be able to like sort of have some start location, some goal location that they're aware of. And then they keep interacting with the environment. By the end of this interaction, like you have a guarantee that you have a navigable structure to get from point A to point B, right? So this would be like sort of a providing motion, sort of providing navigability for themselves and potentially others. So, to turn this into sort of a more abstract version of the problem that we could reason about, there are three things that we need to do, right? We need to figure out how to represent the world. We need to figure out what the actual sort of property is that the robots are trying to achieve. And then also, we need to figure out how we model environmental modifications of these construction steps. So for modeling the structure, because we want to model really irregular environments, we choose to use continuous height functions over, so they're positive over some compact domain. But you know, it can be arbitrarily wiggly. There are no special continuity thing like assumptions on this. So you know, it's a pretty general model that actually allows us to capture much more complex environments than we would be able to using sort of finite discrete elements. And then we say the robot has a particular location on this building domain Q. It's able to modify the environment and then turn this previous height function that was h0 into height function h1. So we get a continuous space, discrete time process to describe the building operation of this robot. So the property that we want to achieve is navigability. So a property of a function that would kind of map intuitively onto navigability for a robot. We're using something, functions, we call them navigable if they're almost locally Lipschitz. So Lipschitz continuity is a pretty standard continuity measure. It means that if I take any 2 points in the domain and connect them by a straight line, this line of that slope should be at most k. That really looks like steepness and is a pretty good measure of like whether or not a robot can drive up. There are sort of two minor modifications to this. One is that once we think about convergence in this function space, it's really easy, you know, like it's easy to have these small discontinuities in this problem. And these small discontinuities, they physically really shouldn't prevent a robot from driving over it. Right? If I have like a small step in there that's like this, like a fraction of the wheel size, then the robot should just be able to drive over it. So that's the almost part, plus epsilon here. And then if we allow that, we also need to sort of limit how close these epsilons can be together. Because if that was our only constraint, you can imagine I have a almost Lipschitz function where just put these epsilons really close together, and then this thing is no longer Lipschitz. Right? right? Or it physically would represent a terrain that the robot cannot go over. So this is a locally checkable global property of a function. So for any 2 points in the building domain, if they're within R, which we think of as like the robot length, the heights of these 2 points can't be more than k times their difference plus an epsilon. And you should think of these as like some parameters. Like you give me a robot platform, and I can give you an epsilon, a k, and an r that would conservatively measure whether or not the robot can drive over this function, or the terrain that's represented by this function. So then the last part is modeling how robots modify the environment. Again, we're going to use a function, and the robot gets to choose some parameters for this function. So here, let's say robots put down these conical depositions. The robot gets to decide where to put down this deposition and how high it is. And then I can model the building process, right, as like applying this operator on some state of the world. The robot gets to choose these shape functions for the depositions. And then the new function is the max of both of those. So I can write down the evolution from hn to hn plus 1. And now I can ask questions like, will this ever stop? What is the state? What will be the state of the functions or the properties when it stops? And I've turned this we've turned this like super horrible problem of like running around and modifying rubble into something that we can reason about. So this is a picture. It doesn't start. So this is now a construction algorithm sort of based on this. And what all the robot does, that's represented by the blue dot, it tries to get to the right side of the screen. All the robot does is like tries to make progress towards this goal. Whenever it finds a point pair that violates the navigability condition, it puts a deposition on the lower of the 2 points. Then it backs up and checks again, because it's entirely possible that like that deposition created other obstacles, right? So you need to go back and check. But if you do that, you can prove that like this method of modifying the environment will always succeed after a finite number of steps. And I can't tell you exactly, what exactly the shape will be at the end. But because I keep monitoring and I keep modifying it, this will eventually succeed. So this is a pretty abstracted version, right? Like robots aren't just dots. Depositions aren't perfect triangles. But even at this very high level, right, like I can now start making like design choices for the whole system, right? Like we're trying to build these actual robotic systems. So for example, right, I can tell you that if a robot has like great suspension and big wheels, then I can make this epsilon bigger. That means my sensor does not need to be as accurate, and I can also use building material that takes up more volume. Similarly, if I have a really really sensitive, really like sort of crappy motion platform, suddenly it has some requirements that directly go onto the sensing, like sort of sensing requirements and manipulation requirements. So we use that then to kind of look at the latest and greatest in robotic technology, so we can pick components to build these robotic systems. I also want to point out that this idea of like Lipschitz continuity and almost locally Lipschitz conditions for navigability directly go from, like I showed all the diagrams in sort of the 1D building domain, but it also goes to 2D building domain, so I get like sort of full 3D construction. So the way this looks, this sort of now mapping this 1D building thing that you saw in an animation onto an actual robotic system. The robot tries to reach this green platform. I'm going to show you a video of this in a minute. But just sort of what goes on is like now the building domain is partitioned into navigable and non-navigable areas. The navigable areas are blue. The non-navigable areas are yellow. And all the robot does is try to like pick the point that gets us as close as possible to the building, to its goal, while staying in the navigable area. This yellow area is non-navigable, but it's also reachable by the robot arm. So these are areas that the robot could potentially modify. So it gets as close as possible and tries to modify a point to grow the navigable area. Similar to the backing up step in the sort of 1D simplified example, it's entirely possible this deposition will not all depositions will like sort of increase the overall navigability, because sometimes I put something up and then I made like a cliff from another direction and stuff becomes non-navigable. But by repeating this process, I can also show that as long as like everything is connected and I can find a path to these areas, that the robot will succeed. So there's a picture of this. So the robot is making all its deposition decisions, and all the graduate students are doing is feeding it more bags, and I think also change the battery ones. But they're always staying outside this sort of exclusion area where the robot is actually making, like constructing stuff over time. So what's not shown here is that this process, well, it succeeds normally. And it's also really robust. Like sometimes you'll see the robot make a mistake on an individual bag, but then like they're missed picking up a bag. But that doesn't really matter because the robot will always kind of reevaluate what the structure is and respond to it, right? This will even work if you go in, like kick everything over halfway through. The robot will just like start over again and start trying to make everything natural.
Can I ask a question?
Yeah.
So is this purely reactive? There's no planning involved?
So the question is this purely reactive, no planning involved? It's as reactive as we can. So there is some planning just for the path planning, right? So between the states, the robot needs to figure out like which bag to pick up, then figure out a motion plan to get there. So that's deliberative planning. But in terms, if you think of the transition from one discrete structure to the next discrete structure, it's purely reactive.
And is that what you're optimizing for?
So this is all for correctness, right? So this is not optimal. So Vivek and Myra, who worked on this, I mean, they spent some time because they were interested in not sitting in the lab for 2 days in a row. So there's some optimization in here, but the whole goal is to really just make sure that like it will succeed eventually, and we're sure that it will that will have the right properties. Oh, and all these rocks are from an actual earthquake testing site. We used to have a lab right next to a giant like house shaker, so we got a lot of free rubble. Mm-hmm.
So for now, the robot is building the ramp, just going forward and direct to the target points. Is there any way like robot can sensing the ground and then maybe make a detour then? So it's less.
Yeah. So let me just repeat the question for everybody. So the question is, right now it just picks like a sort of straight line path to the target point. As opposed to, like, you can imagine, like, if this was a more complicated shape, the robot actually takes a detour, like, longer individual path just so it can get closer. So, I don't remember from the top of my head which one this particular picture is, but we've tried both of those, right? So for us, it's always this sort of discrete transition from, like, one structure to the next, and then within that, we used all our robotics tricks to make it, like, as good as possible. So we have looked at sort of more optimal planning. So you could even, if I could sense all of this, I can even try to figure, like, pre-compute like how much volume I would need to add for different ramps, and then use that to decide on where to start building the ramp. So we've tried, like we've done that. I just don't know which one is right here.
So you made your so for your theoretical guarantees, you have to use the continuous functions, and so I'm assuming that your sensor data is going to be discrete. That's coming in, correct?
Uh-huh.
And so, do you then have problems trying to, like, so for your planner, do you actually have to convert it to a continuous function to then apply your the appropriate deposition? And then B2, or if you don't, then I guess, do you have problems with the error between discrete and continuous?
Great question. So the question is, our sensor, like 3D sensors are necessarily going to be discretized at some point, and our planning is sort of this continuous formulation. So we do have to think about how to discretize, right? So for example, if I have some sensing error epsilon that kind of plays into like what the delta is for the individual discretization cells, and it's kind of something that we have to hand tune at this point. So we want to formulate everything in a continuous space, and then when we implement it, we figure out like what the implications of specific discretizations.
Okay, so that means, so for your actual planner that you're running then, does it, every single planning iteration, does it actually compute a continuous function from the discrete observations, or is it just
continuous, it will work on the discrete approximation of the continuous function, but it will compute the properties that we want.
Okay.
Right,
Okay.
just in its discrete representation.
Got it.
But yeah, so the proofs are all in continuous space, and I think that's like actually one of the nice things, right? Because then it doesn't like, it's kind of like you need to do a little bit of work if I want to map it to a particular sensor, but it's easy to apply to something, to a new environment. So what really makes this work is this really permissive way in which we think of depositions, right? Because we're saying anything that fits under this shape function is fair game. That means we can use a lot of different materials and still like kind of make some formal statements about this. So we can also really easily use multiple materials, because from each robot's perspective, when it sees the environment, it's just like a new height function that it needs to respond to. So we've we've done this. We outfitted different robots with different manipulators so they can manipulate different types of material. And then we can really easily combine these. So one robot makes sort of coarse depositions, and another robot can make both coarse and fine depositions. If we mix these together, we get like sort of much better performance in terms of like the number of steps, right? Because the coarse robot can kind of recognize when it's able to make modifications in the environment. It can make really large modifications that, you know, like sort of volume-wise are equivalent to many small modifications, and then we send this fine coarse robot to sort of clean up the mess that the coarse robot left. So this is it still buffering? Okay, so this is a video of the two robots working. I'm going to not show this in its entirety, just in the interest of time. So this works really well if the structures you want to build are like not sort of too fancy. By too fancy, I mean like have sort of really steep slopes, because then you know, everything we assume in here is sort of like a static world that's just described by the height function, and it shouldn't change between, you know, one discrete step to the next discrete step. And that ends up being like a pretty big assumption. So if we look at the actual surface, because, you know, the robots drive on this and use this function as like use the structure as they're building it, it does deform, right? Because they're all deformable bags. Even if these are rocks, right, like they would kind of compact a little bit. And that kind of violates this assumption. So some of the ongoing work here in this space is trying to figure out if we can still like use the same sort of guarantees and like predictions when, you know, it sort of violates our model in a different way. It's not so much that the depositions are different, it's just like that the world isn't as static as we want it to be when we reason about this. And then the other thing that we're still working on is like, you know, right now we've done this like with 1 and 2 robots, but in theory, like this is all totally reactive, right? And this is something that should be really easy to distribute to many robots. And the things that are kind of difficult there, I think, are related to one of your questions, is that like suddenly now I need to worry about like 2 robots having slightly inconsistent views of the world. So they're both reacting to the environment, but they might do incompatible things because they're actually thinking they're seeing different things, right? So this is something that we can model. So we build a new simulator that kind of like allows us to explicitly address these types of sensing uncertainty.
There's a question online.
Okay.
From Björn Christiansen. It's a little long, so I'm going to paraphrase. Sort of on a more general scale, what's the benefit to actually modifying the environment versus just using, say, a robot with a bigger wheelbase or something that is better at navigating?
What are the benefits? So, great question.
You might need to repeat it.
So the question is like, so what are the benefits of using using this type of environmental modification versus just like getting a better robot that can just drive over stuff? Okay? So I think if you the only thing that you're worried about is the robot getting around, then sure, get a robot that can just drive over everything. But we are also thinking of this as kind of like teams of robots where this is just sort of like like a robot system that you can send into an area that provides navigability for other robots. So it could be that the robot is actually building structures that are like sort of have more stringent navigability constraints than it could deal with, just because there are other robots that you want to send there that end up sort of needing these navigability structures. And if you build the structure this way, right, like the robots could just keep running around and they would just build it and they would also fix it. Right? So this ends up looking a lot like this biological construction, having these properties where I can get this like reactive, adaptive structures, where I get feedback on the functionality, and the robots, like as long as I leave them there, they'll just build it, and they'll fix it, and they'll maintain it, and I can just kind of rely on these properties in the environment. Mm-hmm.
I had a question on the motivation of wanting this sort of distributed, where the robots are not communicating their sense of readings and mapping into some
So
I guess that is biologically inspired, but radio communication between robots is sort of solve problems, so why not leverage that?
sure. So the question is like, why distributed? So I think it's a totally fair question. So I think for these scale of systems, it's I can easily imagine like a centralized scheduler. I can watch 2 or 3 robots, right? I think one of the application areas that like we're targeting with this is sort of like really remote environments where the robots are actually pretty far away, where like communication isn't necessarily a given. So if I had like sort of lunar construction, right? Like I want like the things that are close, of course, like they can coordinate, they could lock each other out and decide together on what to do. But I can easily imagine sort of like larger teams working where like direct communication is pretty limited. In direct communication is limited, and also sort of consistent observations are actually a problem, right? Like because right, to do this centrally, I would need sort of a global, consistent estimate of all the terrain. And that's like kind of easy to do in a lab with like a Vicon system or 3D scanner, but it's pretty easy, it's pretty hard to replicate actually, right? And each robot, even if they can all communicate, right, they would all potentially have like slightly different views of the world based on their own sensor reading. And fusing that in a consistent way is not like trivial. For the discrete space, I think this is also actually a totally fair question. The thing is that, right, like there's even a place, right, like where a single robot could benefit from a more distributed plan, although it's by itself not really a distributed system because it sort of gives me built-in contingencies, right? Like suddenly in my original plan, if it was kind of like this distributed parallel thing, if something doesn't work, I also have like 5 other ways I can make progress, as opposed to like having this like sort of open loop single plan. So it's like comes from the idea of wanting a distributed execution, but even in sort of a single robot following that plan, I get benefits because like I also compute sort of alternative moves for a robot. Yeah. Nobody has really built like lots of like ant-like robots building a brick house yet. So I don't know if the state synchronization is going to be an issue. Probably it's somewhere in between, right? Like probably you do want some things like, if it's easy for me to make decisions without requiring some global knowledge, then why not go that route? And I think if you look at other really big robotic systems like the Amazon warehouse robots, they also have this like, it's not quite a distributed system. It's not a totally centralized system either, right? Like where they kind of figured out what needs to be centralize that, then break it down to smaller problems, and then sort of on the most basic level, like each robot has a little bit of like sort of distributed system, like autonomy for like the sort of really high level safety controls. Yeah, but great question. So the last.
Just to make it easier for people online to see, like clicking the chat link.
Yeah. How are you doing? Sorry, how are you doing in time?
You're doing good. You have about 10, 15 minutes left.
Good, perfect. So the last part is probably the sort of least abstraction that we provide. That comes from the fact that we want to actually send these robots into rubble areas. We figure out how to make great structures with sandbags. But if I want to send a robot into a remote environment, I actually don't want it to have to carry all its building material. Right? The whole point is that I want to send, like, sort of just manipulate the environment. So we looked at different ways in which we can stack rigid objects into sort of stable, large-scale structures. So if we look at that, there are a lot of examples sort of from sort of human construction activities that do this. So these are dry stacked walls from around the world. It's a very old technique. So there are some stone structures that are like sort of from the late Stone Age still around. So it's very stable. They don't use extra stuff, right? And you think it's perfect for robots because robots are super strong. They don't mind super boring work. And why not have robots build these things, right? Because I could just use found materials. So this is from a book that's not actually a reference manual on how to build stone walls. This is just sort of the coffee table book of stone walls, and I do actually think that they're quite pretty. But if you look at these, you see that sort of different human builders use like totally different strategies for building different types of rock walls. And if we look at this, all right, and the reason is like could be preference, but more likely it has to do with like you just find different types of rocks, and like building a good wall, you kind of have to follow a different strategy if you have different types of rocks. So to test this and to kind of like figure out how to like formalize this like autonomous dry stacking a little bit, we looked at different rock walls, and this is like just the 2D face right now because we weren't able to get the like actual 3D shapes of these rocks, and then analyze the sort of shape distribution of the building elements. And you can use a few different ones. So we used sort of how close individual elements are to rectangles, and we used the sort of smallest inner and largest outer rectangle. And if it's 1, it's a rectangle. If it's less, then it's less of a rectangle. The distribution of size distribution within the building elements, right? So if I had a brick wall, these would all be the same size, right? But if I have a lot of really big rocks and small rocks, then I would get a larger spread on there. And then also the aspect ratio, right? Like sometimes you find a lot of really flat rocks, and then you obviously want to like lay them flat. So this is for these 3 building walls. Sort of in terms of these measures, what the distribution of these shape descriptors is, right? And you can see that they definitely overlap, right? But they're also like actually pretty different distributions corresponding to different strategies of rock building rock walls. So the way that we think that we can formalize this a little bit, or make sort of a predictable behavior, is that we have some physical rocks, but then our planner really works on shape distributions, right? And say, I get a new rigid, like irregular element, right? And I just sample it from this particular distribution. And then we want to come up with planners that assemble these elements from a particular shape distribution and put them together into stable objects in a predictable way. And ideally, we also want to figure out sort of how to make this into smaller subproblems that we can use our rock stacking planner on, that we can then put together into really large, useful structures. So it's pretty reasonable, I think, to assume that if I go to a new environment, that I can have some prior knowledge on the shape distribution of rocks that I'm able to find. So there are a lot of rock walls in England. They have a wall building society. So this is a pamphlet, the cover of a pamphlet called Geology for Wallers, that tells you sort of what types of rocks you should be able to find in a particular area of England, and that should influence what type of planner you'd want to use. Or before I send a robot into this environment, I could say something like, all right, I'm going to expect sort of this distribution of rocks, so I'm going to try to come up with building plans that really make good use of this particular type of distribution. On the right, you can see a picture about from, I think it's called the thin section or something. This is from a book called The Lunar Regolith. So there's a lot of studying of the geology of extraterrestrial bodies as well. So even if I send a robot really far away to build stuff on the moon or Mars, right? Like people actually have like spent a lot of time characterizing the geology. So I do have some idea of the objects that I'm able to that I will be able to find, although I couldn't tell you the sort of exact geometry of any particular object, right? And that's something that then we kind of want to use. So we tried a bunch of different things in our group, or mostly Yifang is here too. She tried a bunch of different things in our group to make this work. So here's just some references. We used like heuristics from masonry manuals. So there are a lot of books on how to build stone walls. They give you pretty good heuristics. They're often a little bit difficult to interpret because they say something, all right, pick rocks that are kind of flat, and then put them where they fit well. And you're gonna pick up how to do it. Just build 10 rock walls, and afterwards you'll be able to see it. Yeah? Okay. So then we also tried like reinforcement learning for this. It was a deep Q learning at the time with mixed success. And then we also tried to figure out, like, rather than using like a full-blown physics simulator for figuring out stability, there's some sort of sort of approximate, like sort of approximations you can do if you assume a particular contact geometry that come from sort of vault building and architecture. So it doesn't like don't pay attention to what these actual strategies are called, but basically, on the x-axis is how irregular the material is that we used in this sort of 2D example. And then on the y-axis is the quality of the wall for destructive testing. And basically, over time, we extended these graphs further and further to the right using, like tuning the heuristics, trying to use deep learning to try to, and then using approximate stability analysis in order to kind of effectively use building materials that are more and more irregular. So this was in 2D. We've also done this in 3D. So this is our current setup. And there is an arm that can manipulate rocks. There's a shake table so we can do destructive testing on the actual physical wall. And then there are some cameras to observe this. And we basically have this like system where we like do everything in simulation, then we try to build it, we try to figure out how closely it matches simulation, and we're also trying to figure out sort of why the rock walls fail, and getting better and better at that. So far, sort of the heuristics based on random sampling using a physics simulator are the best approaches we've come up with so far. So we have a library of rocks that we have really nice 3D scans of. These are all the rocks that now have very good 3D representations of them somewhere. These are rock walls that we have planned and built. So this is from a variety of different strategies, looking at like the robot is just kind of like stacking these rock walls together. And then this is sort of the destructive testing of one. So let me start this. And the measure of stability that we're using is sort of from the soft matter world of things, where we're basically giving everything the same disturbance, and then measuring the time for when things fail. And if you put this on a log-log plot for all these types of like sort of weird sort of friction-based, like meshing-based assemblies, we'd expect some sort of behavior in the log-log domain where eventually something will fail. So this is what we're sort of doing for building individual components, right? We want to be able to then take this and generate larger plans, right? Either just like by making sort of these primitives, using our rock stacking strategies to provide these sort of primitive geometric shapes that we can compose, or it's not really clear if that's better, or if we can just sort of directly build large structures using this planner step by step. The next thing that we're trying to do is to actually build these types of rock igloos, which are also called like clochants, based on Gaelic, from where you can find these in Great Britain. And I think we're actually pretty close to building these. I'm not sure how stable they will be, but we'll find out. We'll find out at least for the small ones. But talking of like composal primitives, like if you look at the sort of the pictures of rock walls, there are actually many different strategies, right? And it could be that right now we're just kind of like building these little rectangular rock walls. But there's some other cool sort of things, right? Like where these like sort of sloping lines in there that where the rocks, like you would think they would kind of slide down and actually provide these sort of self-stabilizing V's, so that by just changing the overall strategy, we can probably take advantage of specific features in the rock distribution. All right, so I talked about 3 different abstractions for the environment. If you squint and call this an abstraction, because we just threw the physics simulator directly at it. But here we tried to come up with this like continuous height function, so we get continuous space, discrete time, with a really permissible, like sort of generous model of what modification means, and that allows us to come up with like first high-level algorithms, and then instantiate those with specific robotic systems. And then sort of more on the most traditional side, we also try to figure out sort of mathematical tools we could use for doing assembly in the discrete rigid assembly space. So in general, right, like I think it's super important to think about the representation for the environment if I want to build these sort of embodied algorithms where robots predictably modify their environment. And really what the representation should do is like be an abstraction barrier, so it kind of hides a bunch of physical details that I know I can engineer my way around. Right? And choosing that well is important because it would be easy to make a mistake there where I abstract away too much. I can do beautiful math, I can do fantastic proofs, but I wouldn't be able to build a system that then actually sort of executes the behavior that I've synthesized. And with that, I want to thank two graduate students in particular. Yifang is here, but Vivek is also here. So if you want to talk to Vivek or Yifang, they worked on most of the systems. Yifang worked on the rock stacking. Vivek worked on the little robot that modifies the environment. Aaron and Andrew are also here. They're in my group. And then former lab members, Myra Savoya. She's now a postdoc at NASA. She worked on the rover as well. Jiwon Choi, Walker Gosrick is now a graduate student at UPenn, and Mehdi Shamsi, who is now at Zoox. They were all involved in building these systems. And with that, please ask any more questions. Oh, actually, with that, I'm going to play this video. This is Yifang building giant rock walls with an excavator. It ended up being like pretty hard and really scary. So we didn't build very large walls, but she's super hardcore and has built a lot of rock walls with different systems.
All right. I believe Mason Peck has been holding any questions since the beginning of your.
Oh, I see.
Mason, are you still there? Can you pull up?
Sorry. Can you? I think you should be able to.
I do have a question, if I can.
Yeah, please. Yes.
So just a little bit more about uncertainty and stochastic aspects of this. What would be your approach to maybe formally representing uncertainty in the shapes of the rocks, or maybe the position of the actuator and so forth? Is there a way that your algorithmic approach can embrace that possibility?
Yeah, so I mean, I think it can. I think there are a lot of questions still in the overall process, right? So the shape descriptors, we can use them to like describe objects, right? But they're hard to invert. Like it's hard to take that shape distribution and start generating objects. So we have done some work on taking sort of, artificially generating meshes for rocks that are kind of similar to the rocks we find, mostly by like deformations, like taking different parts of the rocks and kind of like deforming them while they still generally fit the distribution, similar to sort of data augmentation and deep learning, right? Where they're like taking the objects we have and then just like kind of messing with them so they have different contacts. I think it's hard to like the shape descriptors are like reasonable but also kind of arbitrary, and if you read the literature, people often come up with like specific descriptors for a particular application. So we looked a little bit at the sort of angle of stability or angle of repose for different objects, right? And then people try to map that to different sort of physical descriptions of the objects. It's kind of a subjective measure. So I think you would need to come up with a sort of a generative method of generating these rocks, and then you'd probably have to just like actually do some verification or validation that the rocks that you're generating kind of behave the same way as the rocks that you find for the particular question that you're asking. I don't know. I don't think there'd be like a super general answer that will answer everything. I think you'd need to kind of validate your shape distributions. Does that answer your question? Or
Yeah, it does. And I do have a quick follow-up, if that's okay.
Yeah, please.
The quick follow-up is, do you think that there is a way of adapting your approach to reflect how stonemasons chip off little bits of the rock that bothers them, so that you still retain virtually all of it, but you correct for a minor problem that actually makes the whole thing feel a lot better?
Yeah, so I think that would be super helpful. I think we can. You probably be able to identify. I think that would be great. I don't think experimentally that's something we would do, just because I actually, unlike what this picture shows, I really care about the safety of my students, and I wouldn't want robots to have like rock saws or something like that. But I think we can probably do something like that in simulation. I think that the process, right, like would be like right now we're also not really doing the wiggling step, and probably. Right, it will come in where like I think I have a rock that fits pretty well, and then I kind of test its stability in that particular location, and like at that point I can identify that like with a small modification I can make that fit much better. So that's where I would like try the chipping away part, or you could try something where you can try to learn sort of which rocks are really good for assembly, and then sort of automatically use some sort of like, like detection algorithm to detect the features that are just bad you want to get rid of. Like, for example, if something is super flat and has like this big thing sticking out, then that's almost certainly something you'd want to chip off. So you can probably address some of that by just looking at the rock itself or in the context of placing it.
So we're past time.
I have a question.
Yeah, please. Yeah, I can hear you.
Okay. Hi. I have a question regarding to the procedure that you guys are following for the robots. Say if the robot in the current pass did the measurement and went out to pick up a rigid or not rigid object to fill that one up and then remeasure it. So between taking the measure, go pick up the object, say there's another robot who was aiming at the same thing and took the same measurement and already filled that spot. The first robot came back and found that one filled.
Yeah.
How this would react? What I'm trying to actually get is, say if this is a search and rescue operation for robots in aftermath of, say, an earthquake,
Yeah.
and the seismic activity is still not settled down, and you will see change of rubble or change of measurements while doing things. So how this would be accounted for?
So it's a great question. So you're asking, right, what happens if, so I think there are two parts and they're kind of the same problem, right? Like either one robot swooped in and did what I wanted to do, how I'd respond, or even worse, the environment is dynamic and I had a plan, picked up, like found the right thing to put there, and then I come back and something changed. Like even if it's not another robot, it's just still shaking or something.
That's correct.
Yeah.
The collaboration first, and then the second one is
Yeah.
basically change of environment, change of measurement.
Great question. So I think for the robot, the other robot kind of taking your great idea for an assembly move, I think this relates a little bit to the requirement of being distributed. So we normally assume that there's some deconfliction mechanism for the robots that when they're really close, right? So they won't just pile on top of each other or something or bump into each other. And that's normally pretty easy to accomplish on the robotic platform because I can have sort of nearby sensors. But I can still have a situation, right, where they never actually physically close, it's just another one comes in and takes my move. So the model, right, our algorithm doesn't really specify this because it's discrete time, right, and I just assume everything that happens in between is kind of rolled up into this discrete assembly move. If the robot gets an updated measurement of the environment, there should be no problem at all. Because the robot can easily then compute a new placement for the object that it just picked up, right? It could detect, for example, for the navigability condition, right, that the thing that I thought I'm picking up to make more navigable is already navigable, right? So there's no deposition to make. So it's easy for a robot with material to actually to go back and if it has an updated scan to recompute its move. And really what this high-level coordination algorithm gives you, right, is that moves that are based where they didn't reason about each other, right, they're all compatible because they're all sort of locally increasing navigability. And the way they fit together is exactly what the high-level algorithm would do. So if it would be a problem if the robot scans, assumes that computes the next assembly move, then runs off and just blindly executes this algorithm, executes this assembly, right? And it kind of puts a rock on top of another rock without rescanning it. But as long as it gets updated sensor information, it's easy for a robot, even based on local information, to decide what a next good move is.
Thank you.
All right, so as I inform people online,
Yeah.
we are actually past time, so we will have to end up. Let's
Great.
make our speaker one more time.